Hey guys, and welcome back to Physics 101. Today we're going to be talking about gravitation, or just simply gravity. It's obviously one of the most fundamental concepts in physics, and there is a lot to talk about today and a couple tricky questions to go through, so it'll be an adventure for both of us. Let's start with a basic definition that we've got here. I just pulled this straight off Google. If you type in, what is gravity, this is pretty much what you'll get. Gravity is a natural phenomenon by which all things with mass or energy are brought toward or gravitate toward one another. Now, this is 100% correct. Any object that has mass is going to have a gravitational force on other objects. It doesn't matter how small, it could be as small as a tiny little particle. It doesn't matter how big, the Earth, Jupiter, the Sun, whatever. Any object that has mass, which is almost everything, is going to have a gravitational pull or gravitational force on other objects. Now, every object that has mass is going to create a gravitational field. So essentially, magnetism has magnetic fields, electricity has electric fields. Well, gravity also has gravitational fields. Now, if an object lies within another object's gravitational field, it's going to feel a gravitational pull from that object. So on Earth, obviously, everything on Earth is within Earth's gravitational field. Therefore, we get pulled down to Earth if, say, we jump, or we are pretty much pulled by the Earth. Okay, so now that we kind of we have an idea of what gravity is, let's now talk about what determines how strong gravity is. So I've got in bold in here, the strength of gravity is dependent on distance. That's one thing it's dependent on, so let's talk about distance for a second. So when two objects are very close together, that's when the gravitational force between them is going to be the strongest. Now you move them further away from each other, it's going to be quite weak. I mean, this should make sense. When a human's on Earth, obviously the gravitational force on them from the Earth is going to be a lot stronger than, let's say, after they go into space, on a satellite, it's going to be a lot weaker. Or if they go on the moon as an astronaut, obviously then most of the gravitational force they're going to feel is from the moon. Right, so as you can imagine, you push two objects further away from each other, the force that they exert is going to be on each other is going to be less. So this equation here this is Newton's law of gravitation, and it states the relationship between two masses, big M being the bigger mass and smaller m being the smaller mass, of how the force between the objects is related to both the distance between them, which is this r, and this the magnitude of the mass. So yes, distance is one thing that determines magnitude of gravity, and the other is mass. So when we think about, let's say the Earth, obviously its gravitational force on us is going to be a lot stronger than, let's say, a tiny particle. A tiny particle is going to have a gravitational force because it does have mass, although very, very little mass, and so it's going to have a very, very, very small gravitational force on us as well. Even though it is tiny, and even though it is really tiny compared to us, it doesn't matter. It's going to have a force. It's just going to be very, very small. So when we look at this equation here, we can see the two masses on the top half of the equation are obviously going to represent a mass. These are two separate masses, and once you know the two masses of the two separate objects, you'll be able to calculate the forces between them. And G is gravitational constant. We'll get to that in a sec, but it's just a constant. And R squared is the distance between two objects. I think it's important to note that the distance between two objects, you might slip up if you are made to use this equation in a question, because it's not just the distance from one object to another, it's the distance from the center of an object to the center of the other object. So usually in questions it'll be a question about the Earth and a satellite, let's say. You need to know what the radius of the Earth is and the distance between the satellite and the Earth, and add those two up. It's not just the surface of the Earth to the satellite. I hope that makes sense. But it's from the center of both objects, the distance between the center of both objects, center of mass. Okay, enough about that. Now let's get into another term. Now we already established that there are gravitational fields. And what we discuss a lot, rather than, it's quite hard to visualize gravitational fields, but we talk about gravitational field strength a lot. So I've got a definition here. Gravitational field strength at a point is the force per unit mass experienced by a small point mass placed at that point. Okay, now I might have just thrown a lot at you, might not understand straight away. So we've already established that if an object lies within another object's gravitational field, it's going to feel a gravitational force. Right, within the object's field, the strength of that field is going to vary depending on how far away the object is from the original object creating the field, etc. And so we have a definition here. It's the force per unit mass experienced by a small point mass. Okay, so what's a small point mass? All right, I usually call it a test mass, not a point mass. But what it is let's just imagine, the Earth's gravitational field. Now we're going to take a very, very, very small particle or whatever with a very tiny mass and place it somewhere within that field. And once we do that, we're going to calculate what the force is on that tiny particle, or and divide it by that tiny particle's mass. And what that's going to give us is essentially the gravitational field strength at that point. Now the reason it has to be a very tiny and very a particle with very tiny mass is because a test particle or test mass has to have a mass that does not disrupt the gravitational field of the Earth. If we, instead of making it a particle, made it a larger object, that would have an effect on the gravitational field of the Earth, and so we wouldn't really be able to get an accurate value. I've got just a definition here. It pretty much sums up what I just said. It's an object whose physical properties are assumed to be negligible except for the property being studied, in this case mass, which is considered to be insufficient to alter the behavior of the rest of the system. So I hope that kind of makes sense. A test particle, or like I usually say, a test mass, it can't have a mass that is big enough to affect the gravitational field. But we need to know what its mass is, and then we're going to divide the force that's being applied to it somewhere in a field and divide it by that mass, and that'll give us the gravitational field strength at a specific point that we're trying to find. Okay, now keeping on with gravitational field strength, it is actually interesting. We know the acceleration due to gravity on Earth is 9.8 meters per second, and you'll notice that this is the equation here for gravitational field strength. We notice we use lowercase g, and we also use that for the same thing. We use g for acceleration due to Earth's gravity. And so we'll actually see here, this is another formula. These two are both for gravitational field strength. This one is used more to find when we know the distance between the two objects. And I'm going to demonstrate here how gravitational field strength on Earth is the same as the acceleration due to gravity on Earth. So let's do that now. So we're going to use this equation here, because like I said, at the surface of the Earth, it's 9.8 meters per second. And so we know here, because we're going to find out what the radius is of the Earth, and we'll be able to put that into the formula. So let's do this now. So we're going to do the gravitational constant, which I've got listed here, 6.67 times 10 to the power of negative 11 times m, which is the mass of the Earth, times 7. I know it's atrocious handwriting, but I'm sure you will be able to understand what I'm writing. 24 divided by r squared. Okay, now with r squared, remember what I said? It's not, it is the center of the Earth to the surface, which is what we're dealing with here. So we've got the diameter here, but we're going to need to find the radius. So what we're going to do is it's also in kilometers. So first of all, what we're going to do is we're going to divide this whole thing by 2. So we have the radius. And then what we're going to have to do to get it out of kilometers and into just meters, we're going to times it by 10 to the power of 3. And that'll put it in meters, and then we're going to have to solve this whole messy equation here. It's not very nice. It's all long with a bunch of big numbers, but let's get it through, and it should come out to, in just a second, and yep, it comes out to roughly 9.8, which is the same as the acceleration due to Earth. So that should just give you an idea of what gravitational field strength kind of represents. Okay, finally, before we get on to the questions, I just like to look back at these three formulas for a second. I think we all understand the variables. Roughly, we know that an m is going to stand for a mass, F is the gravitational force, and lowercase g is gravitational field strength. Now with these two m's here, you'll notice there's a capital M and a lowercase m often in them. What the big M is always going to stand for is, except in this case when you're trying to find the force, but big M usually stands for the mass that is creating the gravitational field, right? So when we are trying to find gravitational field strength at a point, we're going to use the uppercase M as the mass for the object creating the gravitational field, and then the lowercase m is going to be the point mass, or the sorry, not point mass, test mass. Same thing, but test mass. So with this equation here, if we were given the mass of the test mass, and we knew what the force was acting on it, then we would use this equation to find the gravitational field strength. If we weren't given the test, if we weren't even given a test mass at all, we were just given the mass of the object creating the field, then we would use this equation, because we've got uppercase M, and if we want to find at a certain point, we just have to know the distance between that point and the center of our object. I hope that makes sense. I think that's all we really need to go over for now. If there's anything else, hopefully you'll pick it up along as we go through these questions. Now these questions are tricky, so let's give it our best shot. So we're going to start with this one here. Okay, so the diagram shows a planet near two stars of equal mass m. Each star has a mass 2 times 10 to the power of 30. Sorry, it didn't transfer over onto the page, so I've just got to write 30 here. 30 kilograms. Their centers are separated by a distance of 6.8 times 10 to the power of 11 meters. The planet is at a distance of 6 times 10 to the power of 11 meters from each star. Okay, so we know, oh my goodness, I'm trying to draw a straight line. There we go. So both these lines here are 6 times 10 to the power of 11 meters. Okay, we know that much. And now what we're trying to find here is calculate the magnitude and state the direction of the resultant gravitational field strength at the position of the planet. Okay, now we are going to know, we know that the direction of the gravitational field strength already, because if we think about it, since we're trying to find the gravitational field strength at this point, right, we know what objects are creating the gravitational field are these two stars. So since the stars are creating the field, obviously the direction of the field is going to be towards the stars, right? Because gravity is obviously attractive, and so the direction of the field is going to be downwards. And since these two are both the same mass and the same distance away from the planet, pretty much it's just going to be a straight line down. Right, so we already know the direction, we're already halfway there. Now we're going to calculate the magnitude. Okay, so we're given the mass of the stars, we're not given the mass of the planet. Now we're going to, if we were to treat the planet like the test mass, we would use this equation if we were given the mass of the planet, but we're not. We're given the mass of the object creating the gravitational field, which is the star, so we're going to clearly use this equation. So let's write this out now. I think we can solve this pretty easily. Now there's two separate stars, so we're going to have to, like it says in the question, find the resultant gravitational field strength, but let's just find the field strength due to one star. So gravitational constant times m, which is 2 times 10 to the power of 30, divided by r squared. Now, what's r squared? It's just 6 times 10 to the power of 11 squared. Okay, so now I'm going to have to write this out in my calculator. Yep. Times 2 times 10 to the power of 30 divided by 6 times 10 to the power of negative, 11 squared. Okay, and what we get is 3.7 times 10 to the power of negative 4. It's not meters per second squared. That's, even though that's, the acceleration due to gravity. The units for this, we can just figure it out from here, are just going to be newtons per kilogram. Newtons per kilogram. Okay, so now we have that. Now that's due to one star, right? That's going to be what the field strength is due to one. But now since we have two here, and remember, they're the same mass, and they're the same distance apart from the planet. Now remember what we said, the strength of gravity is determined by distance and mass. And since these are exactly the same, we can just simply double this. So let's double this number, and we simply get, what do we get? 3.7 times negative 4 times 2. We get 7.4 times 10 to the power of negative 4 newtons per kilogram. Right, so that should make sense. But now what we have to do, because this is where it gets tricky, if there was just one planet, if there was just one star, we could just draw a straight line from the star to the planet and consider that the direction of the gravitational field strength, and it would be a lot more simpler. But now that we have two, and again, we're going to have a resultant gravitational field strength, we're not done. This is not our final answer. What we have to consider are the angles that the planet is making with the star, and this is where it gets tricky. So we're going to have to find this angle. Oh my goodness, I know that is terrible. And what our final resultant field strength is going to look like is this, 2g cosine theta. So we got to find these angles, and then we got to put that angle into this formula. So what we're going to do is, well, straight away we already know what this angle is, and we know what this angle is. It's not angle, sorry, this length, right? Because the whole thing is 6.8 times 10 to the power of 11 meters. So that means 1/2 of it is just going to be that, and the other half is just going to be that. Right, so let's just do our little trigonometry here. So opposite is this one, and hypotenuse is this one, so we're going to use sine, the inverse of sine, 3.4 times 10 to the power of 11 divided by 6 times 10 to the power of 11. And what we get, I'll write it out just so you guys can see. Oops. 3.4. We can just take off the times 10 to the power of 11s. And what we get equals sine 30. Oh, not so, sorry. We get 34 degrees. And so we're going to put that in here. So we already have our 2g, 7.4 times 10 to the power of negative 4 times cosine 34. So let's do that now. Negative 4 times cosine 34. And what we get is 6.1 times 10 to the power of negative 4 newtons per kilogram. Okay, so I think the first half of this whole equation was quite simple, just putting it into the formula. The direction should make sense, the direction is obviously going to be downwards because gravity is attractive, so it's going to pull. These two stars are going to pull the planet towards it. But since we have two stars, both separate distances away but equal and same masses, it's going to just be straight down. It wouldn't be, down here, or it wouldn't be any other direction. That wouldn't make any sense because they're going to have equivalent field strengths at that point. It's just going to be straight down. Okay, so that's that whole question done. Now we got to get into this question. Now this question I feel is even more difficult. So a planet has radius r. At a distance h above the surface of the planet, the gravitational field strength is g, and the gravitational potential is v. Show that v equals negative g bracket r plus h. Okay, so there's a lot to do here, but let's start off with the basics. So gravitational potential. Now we know gravitational potential energy, the same thing, it just left off the word energy, is mg change in h. Now we know that much. Now we also know gravitational field strength is, we've got it listed here, g equals F over m, and g also equals gm over r squared. Okay, so we're going to use these three equations, definitely. Might even have to use the third equation, but let's just keep these three for now. And so we're going to have to show that the potential equals negative g r plus h. Okay, so let's just start, because we know since we're trying to find gravitational potential, let's start with this equation here. So we're just going to call it v, because that's what it has listed in the question. So v equals m. Now m, think about gravitational potential energy. We talked about this last video. M in this case is the mass of the test mass, right? Or the object that's being influenced by another object's gravity. So you know, when you think of a ball, its gravitational potential energy is determined by its vertical height on the surface of the Earth. So we're going to call this ms, which just means we're going to call it test small mass or test mass. I can draw an S. There we go. So m subscript s. We're just going to leave that as that and call it, you know, the smaller mass or the test mass. Now g is just going to be the same. It's going to be g, and then change in h. It has listed. Okay, now what are we going to write for change in h or height? So planet has a radius r. So obviously we're going to use that radius. We're going to tack that on to the distance from the point we're measuring. So it's a distance h above the surface of the planet. So straight away we already know we're going to add r to that value, because it's from the center of the planet to that point. Remember, not the surface of the planet. Okay, so already straight away we can kind of see this resembles this here, this formula here. But we're not done yet, so we're going to have to get rid of this small ms nonsense, and then it's pretty much done. We're going to have to get a negative sign, but that's more conceptual than algebraic. So now what are we going to do? Well, we have our formulas here. Why don't we sub one of these formulas in for g? So v equals m subscript s. Now g, let's do this one. This is a lowercase m, and that's going to cancel out this. So equals f over ms h. Well, we'll just do it in the order that the question has it. Right. So now we have this, and these two are just going to cancel out. So we're left with v equals f r plus h. Okay, so this is what we're left with. So where do we go from here? So we have f, but we clearly need to rearrange this somehow. So we're going to use one of these equations here for f. Now clearly we don't have, where is it? We need to use this equation here. So let's write that in. So v equals g mb, big mass, ms over r squared, which is going to be r plus h squared. Oh, that should be a lowercase, I'm sorry. and then this is all times by r plus h. Okay, so now we're getting further down the track. It seems to be getting more confusing, but it won't be. So now we've got to do this, change this again into v equals g m b m s over r plus h, right? Because one of these is going to cancel out. This is going to change to a 1. Okay, so now this is what we've got. This is what we're left with. We've got the potential equals this nonsense. So now that we have this nonsense, now what we're going to do is actually replace, we're going to replace this with one of the other equations. So we know that g equals, this is where it can be a bit tricky. Now there are multiple ways to approach this question, but this is the way I've chosen. So we're going to use the other equation, this equation here, g equals gmb over r plus h squared. R plus h squared. Is that right? Yeah. Okay, so now we have these two equations here. This is the equation we really want. And we also have this one just straight from a booklet or the formula sheet. So now what we're going to do is combine these two equations. So obviously they're pretty similar, as we can see. So why don't we replace or get g into this equation here, right? So we're going to say that v equals g. Now g is going to equal this nonsense. But what we're going to have to do is make it so that these two are exactly the same. So ms is missing from this one, so we're going to add ms. And we have an extra r plus h in this one, so we're going to add r plus h. Okay, and so now kind of just done a loop here, but what we've effectively done is this, this is the important formula that we needed to derive. And now that we have this, now we have to sit back and think, all right, we're back to kind of where we started. So what are we missing? Well, we have to remember ms here stands for the test mass, or this, you understand what I'm saying, is the gravitational field strength at this point. In the question, there is no mass at this point, right? We're just trying to find what the strength is at this point. And because of that, there is not going to be no mass at all. So we can just get rid of that, because it's not that the mass is 0, otherwise we put in a 0 for this. It's just that there's no mass that we're using to calculate this gravitational field strength. And so what we're going to be left with is g r plus h. Okay, and so now this looks very similar to this question, but now there's a negative sign. And the reason there's a negative sign, you would just add the negative sign, is because when we talk about gravitational potential in terms of planets, is because when we talk about gravitational potential between planets, the maximum potential distance that the two objects would be apart is infinity. Okay, and when these two planets are at an infinite distance away, the gravitational potential is going to be ideally 0. So because of this, right, because of this, if the maximum is 0, that means all values are going to be negative. If the maximum is 0, we're going to have numbers that are constantly negative all the way up to negative 0.001 until it finally gets to 0, which would be infinity. Now, if you're confused as to, well, why didn't we talk about this in the last video when we were talking about objects above the Earth's surface? So when we have objects on Earth, right, we consider an object on the surface of the Earth to be 0, having 0 gravitational potential energy. So the reason we have positive gravitational potential energies for objects on Earth is because when you think about an object on the surface of the Earth, at that stage, that object has 0 gravitational potential energy. And so any values above that is going to be positive. Now when we talk about mainly planets, we consider those to have negative gravitational potential, because at an infinite distance apart, those are going to be 0 in terms of gravitational potential. So let me just draw this out. I don't have much space, but I'm just going to draw it out here. Let me just get rid of this, sorry. So when two objects are, let's say this is the distance between the two planets, right? At this distance, it's going to be a negative value. Now the reason for that is because if these two planets were an infinite distance apart, the gravitational potential would be 0. This can be a bit confusing to understand, but just I think if you remember that when we talk about objects on Earth or related to Earth, it's usually going to be a positive value in terms of gravitational potential, because when we have an object on the surface of the Earth, it does have 0 potential energy. And so when you raise that, it's going to be positive. Whereas, when we talk about planets, they're never going to be 100% touching each other. And so the maximum separation is going to be considered infinity, and at that stage, it's going to have 0 potential energy. And so once we move these two planets further away from each other, we're going to have a negative value because we're working upwards towards 0, if that makes sense, in the negative numbers towards 0. That might be a bit confusing, but hopefully I've explained it a bit. It's just the value of the potential energy is going to be negative, not the value for G. I hope I made that clear. It's not the value of G being negative, it's just you add on a negative sign, so the entire value, once you put in the variables, is going to make the potential energy negative. I think I've explained things good enough. If I haven't, always email me. It's in the description below, and I can answer any more questions, or just look up more videos online. Hopefully you'll find one that explains it very well. I didn't really have enough time to explain it that much here, but it is just something to keep in mind. Just remember, gravitational potential is negative, when you're dealing with planetary magnitudes of planetary size. Okay, that's it for this video. Thanks for watching, and I'll catch you guys in the next video. Till then.